Hi, welcome back to Statistics 1. We're up to Lecture 6, and today what we'll do is some correlation analyses in R. In the last two lectures, we spent a lot of time talking about correlations. In Lecture 4, I did a basic introduction to correlations and walked through the calculations of the correlation coefficient. We talked about assumptions underlying the correlation analysis. And then in Lecture 5, we talked a lot about measurement theory and the idea of testing reliability and validity of our measures. And one way to do that is to look at correlations. So today what we'll do is look at correlation analysis in R. So we'll write a script in R to do some correlations. This lecture is organized into two segments. In the first segment, we'll do some scatterplots and correlation analyses. And in the second segment, we'll actually do test-retest reliability estimates from the example that we're using in segment 1. So I simulated enough data that we could actually do this test-retest method for assessing the reliability of several variables. So let's start the first segment, and that's just to write a script in R that does scatterplots and correlations. The goal of this script, and again, in these types of lectures where I'm walking through R code and showing you R functions, you should try to follow along and download the data and try and write the script that I'm constructing as we go through the lecture. And then at the end of the segment, I'll show you the finalized script, and you can see if your script matches the one that I have, and you can execute it, and you should get the same output, the same graphics, the same statistics, etc. So the goal for today's script, the ultimate goal, of course, is to get the correlation matrix. But before we do that, we want to get histograms for all our variables. We want to look at descriptive statistics, and we want to look at scatter plots because we need to test all the assumptions underlying a correlation analysis. And these will allow us to look at the assumptions. So histograms will let us know if our variables are normally distributed or not. The descriptive statistics will help with that as well. And then the scatter plots will allow us to see whether we have linear relations between our variables, and they'll also allow us to see if we have homoskedasticity. Remember, that was one of the important assumptions underlying correlation analysis. So the example I'm going to use for this segment and for this script are data from an online assessment tool called Impact. And Impact is a computerized neuropsychological assessment of memory and attention. And they have a website. If you Google Impact, you can find their website and find out more about their measures. Impact is very popular. It's used all over the world. It's used primarily in the US. And it's primarily used to assess the cognitive effects of head trauma. And its primary use is for assessing the effects of sports-related concussion. So in high schools and in universities in the United States, if athletes suffer a concussion, a lot of the coaches or athletic directors will have the athlete perform the tests on this Impact website to see if their short-term memory and their attention is compromised at all as a result of the injury. So as I said, you can Google this website. It's Impact. If you just Google impact.com, it tells you a lot about the assessments. And the reason I picked this image because it's right on the front first page when you Google their website. It says valid, reliable, safe. So we'll see about that. Let's run some analyses and see if it's actually valid and reliable. Safe, okay. We can't test that with our statistics. But we can look and do some validity and reliability analyses. So the way the Impact works is it actually creates lots of subscores from lots of little tests that it gives individuals as they perform the tasks on the website. But it generates 5 composite scores. And according to their website, it measures 5 different constructs. So verbal memory, visual motor speed, a general reaction time, and impulse control. And I don't have time to show you all the different tasks that they use to get these composite scores. if you're interested in this type of assessment, I just recommend you go to that website. They provide lots of details about how they get these scores. What we'll do is we'll analyze some data that were simulated based on real data that we have here at Princeton. So these aren't the real data, but I simulated the data to look like what we have at Princeton. So at Princeton University, we are engaged in a pretty large-scale project to look at the effects of concussions in our athletes. So a lot of our athletes go to this impact website and they actually take the tests. And a lot of our athletes do this when they first arrive at Princeton, and we call that their baseline tests. And then we have some of them do it again, just so we can look at test, retest reliability. Of course, then we have athletes do it if they suffer a concussion as well. And if we have baseline on them, then we can see if their performance is suffering relative to their baseline. So I put some data on the course website in a file called stats1 example2.txt. This is the second example that I've covered in a lecture. So again, our goal is to write a script to do some correlation analyses. Specifically, what we want to do is look at the correlations among those 5 composite measures that impact gave us. We have 200 students who took the tests, so we have a data matrix that has 200 rows, 1 row for each subject, and 5 columns, 1 column for each variable. And if this is at all valid, at all reliable, we should see some degree of correlation among the measures. For example, verbal memory and visual memory should demonstrate some degree of correlation. So that's what we're looking for. It's just correlations among the main composite measures. But first, as I like to do, let's start off a script with just some comments. So I just put in, this is Statistics 1, Lecture 6, an example script. We're going to do a lot of things in this script. We're going to read data, we're going to plot histograms, we're going to get descriptive statistics, we're going to look at scatterplots, and finally get the correlation matrix. So the first step is just to read the data in. So again, like we did with previous examples and as you've done on assignments, we'll use the read table function in R. So I'm using the read table function and putting my data into an object called impact. And I just made up that name, impact. Again, the header equals T means header is true. That means the top row of my data file, stats1.ex.o2.txt, the top row of that data file has the variable names in it. It doesn't actually have data in it, so it's a header. So the header equals true. And this doesn't necessarily have to go into your final script. But if you like, you can, if you're still trying to get used to objects and data frames in R, then explore the contents of that data frame. So class, remember, is a function that tells you what type of object is this impact. And R will tell you this is a data frame. If you use the function names, R will tell you the names of all the variables or the column headings that were in our header. Onto the stuff that actually goes into the final script and that we would want to run if these were real analyses with real data on a regular research project. First thing we might want to do is get descriptive statistics, right? So histograms and summary statistics. So what I'm showing you here is just a line of code to get one histogram. I'm not going to go through repeatedly and do it 5 times, but you can just repeat this. And I got a little fancy this time, so I added in some labels and I added in color. So this first histogram, what it's doing is it's plotting the data frame impact. Remember, $sign tells it what variable to grab from impact. So memory.visual is one of the variables. That's the visual memory composite score. And then I've just put labels on here. So I labeled the x-axis visual memory. I just put a main label for the entire graph called histogram. And I made the bars in the histogram red. And you can see what that looks like in the next slide. This is the output from my script in R. You see that we're plotting visual memory scores. They're on a scale of 0 to 100. And what you see is we have a sort of negatively skewed distribution. And this is true of several of these composite scores in the impact assessment device. And that's probably because we're dealing with Princeton University students, right? They were pre-selected to come here on the basis of cognitive ability. So it's not too surprising that they're maxing out on these sort of simple visual and verbal memory tasks. Remember, a lot of the users of the Impact website are high school athletic programs. So it's not surprising that we're getting a little bit of a ceiling effect among our Princeton students. So way to go, Princeton students, in acing this test. Not good for us as statisticians, though, right? Because we've got a slightly skewed distribution. Some people are maxing out on the scale. That's reducing our variance. That reduces our chance for covariance or correlation. So it's not great for experimental purposes, and we'll see how it impacts the correlations in a moment. So again, I'm not going to list the code for all the histograms, but you could do it for every single composite measure. There are 5. You'll see it in the final script. The other thing we can do real quickly, though, is get summary statistics. And that's just, again, the describe function. We've used this several times now. So just describe impact gives me lots of summary statistics for the variables in that data frame. So we have verbal memory, visual motor speed, then there's a general speed, and there's impulse control. You can see that there's 200 students who took this. Again, these are simulated data based on the real data. So I just simulated 200. We've actually had, I think, over 400 Princeton students complete this impact thing. It's pretty impressive. A lot of credit goes to our athletic department, especially the football program, for keeping up with this. And then you see the measure of central tendency, the mean, you see standard deviation, and so on. Again, you're seeing sort of a ceiling effect in these memory tasks, especially the verbal memory task, and a little bit of skew in some of the measures, but really nothing too bad. Typically, if skew is less than 3, absolute value 3, then it doesn't really raise a red flag. So the next thing we want to do is look at scatterplots. So the descriptives, the histograms, descriptives, that allowed us to test the assumption of normal distributions, right? But we have to look at scatterplots to see if we have linear relationships and to see if we have homoskedasticity. So the way to do scatterplots, this is a new function for us, is just the function plot, and then put in the y variable, then tilde. What I mean by tilde is that symbol there, and then the x variable. So just y tilde x. So again, I'm referencing the impact data frame. I'm putting the verbal memory variable on the y-axis. That's arbitrary. I just picked that at random. And put the visual memory variable on the x-axis. I'm assuming that these two variables are going to be correlated. They're both measuring sort of short-term memory. Again, then I put some labels on there. So a main label, a scatterplot, and I labeled the axes. Another nice thing to do is to plot the regression line through that scatterplot. So remember, the regression line just goes through the scatterplot or through the dots to minimize the distance between each dot and the line, as to minimize the sum of squared residuals. Remember, that's the idea of ordinary least squares. And the way to do that is to use the LM function. We'll use the LM function a lot as we go ahead and start doing regression and multiple regression in the next few lectures. So LM just stands for linear model. And what we're doing is LM, the y variable, tilde, the x variable. And then I colored the regression line blue. Let's just see what that looks like. It's easier to just see it in a graph. So again, on the x-axis, I have the visual memory variable. On the y-axis, verbal memory. And I just called this scatterplot. And the blue line is showing the regression line. That is, it's trying to minimize the distance, the overall distance, between each dot and that line. One thing you should notice when looking at this scatter plot is that ceiling effect in the verbal memory task, right? There's a lot of people who are just sort of hovering there right around perfect. Again, that's showing the negative skew in the verbal memory measure. But still, we have a nice positive correlation between the two memory tasks, and it doesn't look too awful. Again, I could do that for each pair of variables, but I'm going to save that for the final script. Let's move to getting the actual correlations. So there's several ways you can get correlations. So one is just the function core, C-O-R. So I can just do core x, comma, y. So core impact memory verbal with impact memory visual, and that will just return the correlation coefficient. I could also do the same thing, but ask for a significance test. And we're going to spend a lot of time talking about what the significance test means and other information that you should report along with it. But I thought I'd just show you what the output looks like for core.test for one pair of variables. So here's the output from R for core.test, that function. And as I suspected, there's a positive correlation between verbal memory and visual memory. So the correlation is down here. It's a positive 0.45. That was reflected in that positive slope of the regression line in the scatter plot. R gives you lots of other things that we'll talk about as we talk in more detail about null hypothesis significance testing and confidence intervals. What this is showing is a couple of things to point out is there's 198 degrees of freedom. What does that mean? Well, that's the number of data points in this correlation analysis. There's a free to vary. So if you remember the formula for the correlation coefficient, we calculated the sum of cross products by getting deviation scores on x and deviation scores on y. So if I know all the deviation scores on x, and I know the mean of x, then the last data point in that distribution is determined by those other values that I already know. So the number of values that are free to vary in any distribution is always n minus 1. So there's n minus 1 in the x variable and n minus 1 in the y variable. So we had 200 cases. So it's 200 minus 2. We have 198 degrees of freedom. R gives you a p-value. This is significant digits out here to 11 significant digits. That means the probability of getting this correlation of 0.45, given the assumption that there's no relationship, that's null hypothesis significance testing, the probability of that happening is really, really low. It's really unlikely. So what this means is we could reject the null hypothesis and we would say that this is a statistically significant correlation. A lot of people don't like that approach, and we'll talk about why in later lectures. So another thing we could do is just report what's called a confidence interval. Remember that every sample statistic is prone to sampling error. So this correlation coefficient is only true for this sample. If I ran another 200 students, I might not get 0.45. I might get 0.48. I might get 0.39. There'll be some fluctuation. The 95% confidence interval gives you some idea about how much fluctuation to expect. So this is saying we can be 95% confident that the correlation is going to fall somewhere between 0.33 and 0.55. So we can be safe to assume that this visual memory task and this verbal memory task, they're correlated. They're showing some validity, and that's actually showing some reliability. They're measuring something real. It's quicker to just do all the correlations in a matrix, and I can just do that by using the function core again and then putting the whole data frame in there. This works for this object impact because it's a data frame that contains all continuous variables in all my columns. If I had some string variables in there, if I had missing values in there, this wouldn't work. But since I have a full data set that's all continuous, this will work, and it will give me all the correlations in a nice matrix. So I ran that in R, and this is what a correlation matrix looks like. You've seen this in previous lectures, and hopefully you've seen this in research reports. So remember, a correlation matrix on the diagonal is ones, because that's the correlation, one variable with itself, and it's symmetrical. So you see that this 0.45 entry, that's the correlation we just looked at, is the same as this 0.45 entry right there. So you only have to look either below the diagonal or above. For some reason, I always look below. I guess that makes me a pessimist, even though I'm not. I think it might be psychological association style. That's why I look at that. But what you see is correlations where you should see them. So the memory tasks are correlated. So verbal memory is correlated with visual memory. The two speed tasks are correlated. So visual motor speed is correlated with general speed. And that I see that right here. That correlation is negative because the visual motor speed is measured on a scale to reflect higher scores mean better speed, faster speed, and the general speed measure is the opposite. So you see positive correlations with speed, vis motor, and the memory tasks where, again, higher scores are better. But you see negative correlations with the general speed measure. Then you also see, again, correlations where you should see them. So the visual motor speed measure is correlated with visual memory at 0.37. So this is showing some validity in this impact assessment tool. What's not looking so hot is impulse control. So look at the bottom row of this correlation matrix. You got a little bit of a correlation here, but then the rest of the way, not much. And in the next segment of this lecture, we'll do a reliability analysis, and you'll see that the impulse control measure isn't so reliable. And that could be why it's not correlating with much. So I just added in one more sort of fancy piece of code to show you sort of the power of R. This is just skimming the surface. But it allows us to do what's called a scatterplot matrix. So we have, just like the correlation matrix, we can do lots of scatterplots all together in one matrix. But it's just like a correlation matrix in that the diagonals just tell me what variable names there are, and then the correlations are colored and ordered according to magnitude. So what you see here are like memory verbal and memory visual. You see the scatter plot for that correlation. That's the one that we actually looked at. And that's one of the stronger correlations, so it's colored in sort of a pinkish color. You also see that the two speed measures are correlating highly with each other. What's off to the side, or sort of the fringe of this scatter plot, is impulse control, because it doesn't correlate well with any of the other measures. And that's reflected in just looking at the scatter plots and looking at the colors of the matrix. So to wrap all this up, let's look at the final script. These are all the things that should go into the final script. You could save this and rerun it at any time, and you'll get all of that output. So you'll get histograms, descriptive statistics, scatter plots, and the correlation matrix, and that fancy color graphic. I put the code in at the end here. So I broke this up into bits so you could see it on the video. I used the library psych for most of this. We did the read table command. I explored the data frame. I also played around with the default settings in the graphics. So you can do that with the PAR function. And I encourage you to just explore R and see what the different default options are. I'm doing that because I'm displaying graphics sort of on a big screen, so I needed to change a lot of my default settings. I plotted a bunch of histograms using the hist function. I did descriptives using the describe function. You should be getting used to those by now. Scatter plots, this was new. We used plot, LM, and AB line. And then correlations, we could use the core.test function or the core function. And then finally, I'm showing you the code that I used to get that fancy graphic So I'm running a little long in this segment. I'm not going to walk you through all of this code, but if you just reproduce this code, you can get the same type of graphic, and you can use it for any data set where you'd want to run a large correlation matrix like this. And it will order your correlations and your scatter plots by magnitude and color them by magnitude.